Okay, so we're going to take a look at some practice problems that have direct connection to some of the concepts that we've talked through during the last two sessions. And so one of the first ones that we're going to look at are pH and buffers and some of the calculations that are involved there. And then we're going to explore molarity and osmolarity. And then we're going to wrap up with a look at acidosis, alkalosis, and the anion gap. So if you consider what we know about acids and bases, from general chemistry, you would recall that there are strong acids and weak acids. And so the key difference here is that strong means that that compound in water is 100% ionized. So for example, HCl completely dissolves in water, forming H plus and Cl minus, or if you prefer H3O plus because of the interaction with water, the hydronium. And so we can represent that generically using HA going to H plus and A minus, where that could serve for any acid. And so if we know that 100% of our HA molecules dissociate in solution, then we know that the concentration of the H plus is going to be equal to whatever the concentration of our acid was to start with. That means all of the acid dissociate, so there's no acid molecules left. All of them have been converted to H plus. So a typical problem would be to calculate the pH of a 0.1 molar solution of HCl. And we care about this because gastric juice, the liquid that's found within our stomach, of which there's a range usually somewhere between 0.05 to 0.1 molar, of which we generate about 1.5 liters a day, is what's responsible for activating our digestive enzymes. And so when we do this calculation, all we're really looking at is a direct corollary between the concentration of our HCl, which then becomes the concentration of our H plus. So we take the negative log of that number, and that gives us our pH. And in the intestines then, this acid gets neutralized by sodium bicarbonate. So strong acids are pretty rare for us to find within the human body. They're really localized only to our stomach, and so outside of that environment, we know that a pH of 7.4 is a little bit more likely to exist, although there are some differences within other protein environments. But this would be an example of where we would see a calculation for a strong acid within the context of biochemistry. Now, if we think about weak acids, those are actually far more prevalent. And so there are several different examples of weak acids that we could look at, but a great hallmark would be acetic acid. And so acetic acid, it's important to note that before we talk about this, these constants, Kc, Kw, Ka, and Kb, are all going to be temperature dependent. And it's important for us to also recognize that for what we're talking about right now, that's going to be at 25 degrees Celsius, or what we think of as a standard temperature. And so for weak acids, these are going to be less than 100% ionized in solution. And so you can think about that in terms of, right, the diagram that I've shown here. So, right, if I put a strong acid into solution, you'll notice that all of the white and all of the red, right, the proton and the negative ion, completely separate. Whereas for a weak acid, you're actually going to notice that in solution, the predominant form is actually the acid itself. There's not as much dissociation into the proton and the negative ion. And so if we think about acetic acid, we have formula HC2H3O2 as our example. We could also represent it as CH3COOH. And when that dissociates into solution, we have our proton and then our conjugate base. The conjugate base in this case is going to be the acetate. So if we think about that from a calculation standpoint, we understand that, right, our acetic acid can interact with water to form H3O plus and our acetate. And if we go through and take a look at that, we can write an equilibrium expression where our products, H3O plus and the acetate, divided by our starting materials, in this case, the acetic acid and the water. Now, you are probably familiar with this from general chemistry. Whenever you're writing equilibrium expressions, you discount pure water. Why would you do that? Well, in this case, in pure liquid water, the concentration of water is going to be a constant value. And if you're like, well, how do you know that? So consider 1,000 milliliters of water with a density of 1.0 grams per mil. And so that 1 liter would weigh 1,000 grams. And if I were to take that mass and then divide it by the molecular weight of water, that's going to give me 55.5 moles. The molarity of this water would then be 55.5 moles divided by 1 liter, or 55.5. And the solutions that we study, say, for example, in introductory chemistry, are so dilute that the concentration of water is unaffected. And so, because typically we're dealing with dilute solutions in living organisms, the concentration of water is also going to be unaffected. So that 55.5 is a constant, and therefore we can exclude it from our expression, which is what you see in the Kc. And so this Kc times H2O is what we represent as Ka. And so this is the acid ionization constant, and it's determined experimentally, and each acid is going to have a unique value. So for example, acetic acid's value is going to be 1.77 times 10 to the negative fifth, or somewhere in that range. Now, if I were to take that and think about it in terms of the context of a problem, what is the pH of a 0.1 molar solution of acetic acid? Well, I can do that calculation. So I can use my generic acid formula and go through and come up with a Ka expression. And what I want to do is recognize that I need to know my H3O+. I don't know what that is. And so once I have that, then I can do my calculation. And so you can do an icebox if that's something that you feel more comfortable doing. But essentially, I'm going to represent my unknowns with x's. And in this case, right, my acetate is also an x because there's a 1-to-1 molar ratio between my H3O+ and my AC-. And that's going to be created as my acid dissociates. So I come up with an expression substituting in x for the two things that I don't know. And now I've got, right, my HA. So what happens to my HA? Well, however much products appear, that's how much reactants have to disappear. And so that's why I say minus x. And this is going to result in a quadratic equation, and you could solve it using the quadratic formula, but we're actually going to use a trick to make our calculations easier. So K's are approximate, and most have an error of about plus or minus 5%. So as long as the change is approximately 5%, we can actually simplify our expression. So we're going to remove that minus x piece, and now it's very simple to solve for our x. Now, two really important things here. The Ka value is going to be unitless, but the quantity x is actually a molarity. So make sure you're using the right units for molarity. And then make sure that you're taking the square root of both sides. And finally, we'll wrap up by taking the negative log of x to get our final answer of 2.876. Now, it's useful, I think, to do the mental check and actually look at that 5% rule. Did my answer actually fall as less than 5%? And I can do that by taking my concentration of my H3O+ over my concentration of my acid and multiply that by 100. And in that case, it ended up as 1.33%, which is more than acceptable. So you can see here the way that I would use my equilibrium constant, Ka, to be able to calculate the concentration of my H3O+, and then how I could use the concentration of my H3O+ to figure out my pH. So let's take a look then at weak acids and the salts. So if I take sodium acetate, right, that would be a prototypical salt of a weak acid. And if I use the shorthand of NaA, where A- is going to stand for my acetate anion, then I have a chemical reaction or a net ionic expression for the hydrolysis of this salt, my NaA. And so if I do that, you're going to notice I have my acetate reacting with water, and that's going to form an acid. Now, you are going to write that as an equilibrium expression. And in this case, A-, the acetate, is acting as a base. It accepted a proton from water. That means that we can write a Kb expression for A-. And now we come to this really important piece where we know how to calculate Kb because we know the relationship between Ka and Kb, and we know the value for Kw. So I know what the Ka for acetic acid is. We talked about that previously. And I know what the Kw is for water. So I can use, right, 2 of the 3 to be able to find the third. And so by knowing what my Kb is, right, then you can use this expression to be able to calculate your unknown concentrations and then calculate POH and pH, or, right, be able to utilize that information, say, for example, to understand the concentration of the acid that's produced. And so we can do this for any salt of a weak acid if you know the Ka. And you're probably astute enough at this point to recognize that then the salts of weak bases are going to be acids. So you can do a similar type of expression for that. So let's talk about how pH and buffers, right, correlate. And so a buffer is going to be prepared by taking an acid and its salt. So in this case, acetic acid and sodium acetate. And if I combine those two and I wanted to know what the pH would be, I would have to look at using the Henderson-Hasselbalch expression. So that's where I would be able to use my Ka to determine my pKa. Again, that's just taking the negative log of my Ka expression. And that's going to give me a value for my acetic acid. Then we're going to take whatever information we're given from the problem and plug it into our Henderson-Hasselbalch equation. So in this case, right, we've got our pKa that we plugged in. We plugged in the concentration of our acetate. We plugged in the concentration of our acid. Since the log of 1 is going to be 0, then our pH is actually equal to our pKa, in this case 4.752. Now, the pH of this buffer is not the pH of a solution of acetic acid alone. It's acetic acid and the salt. And you know that because if you were to go through and calculate the pH of a 1 molar solution of acetic acid, that would be 2.376. Our pH is 4.752. The pH is less than the solution of just the pure acid. And that's true because of Le Chatelier's principle. So if we look at the dissociation equation for acetic acid, right, we understand now that increasing the concentration of the acetate pushes the equilibrium back to the left. That means that's decreasing the concentration of H+. That's going to make the solution less acidic, making the pH of the buffer larger than the pure acid solution. And that's important because the whole point of a buffer is that I'm able to add acid or base and maintain a pH within a certain range. And so buffers have capacities, right, outside of really one value pH-wise on either side, right, of the pKa. It loses that ability. But within that context, buffers are highly effective at maintaining pH. So we're going to transition a little bit and look at some practice problems looking at molarity and osmolarity. And so if I wanted to know how many millimoles per liter of sodium are present in a 0.9% sodium chloride solution, right, I could go through and talk about how I would do that. But I want to talk about context for a moment because this 0.9% sodium chloride solution is actually the saline solution. It's what is commonly used, say, for example, if you're adding eye drops and have contact lenses. It's also what can be put into an IV drip bag. So there's very common applications for the calculations that we're doing right now. And so if I take a look at sodium chloride, that dissociates into the sodium and the chloride ions. And that 0.9% sodium chloride is going to contain 0.9 grams of NaCl per 100 milliliters of water. And you may be wondering, well, how did you know that? Well, because this is a percentage, right? I make the assumption that if I had 100 grams, then I would have 0.9 grams of NaCl per 100 milliliters of water. And it's 100 milliliters of water because, again, the density of water is 1 gram per milliliter. So that's effectively 100 grams. Now, I could also think of that in a larger scale, so 9 grams per liter. I could look up from a periodic table, right, what the molecular weight of sodium is and what the molecular weight of chloride is, and that's, if I add them together to figure out my overall molecular weight, that gives me 58.5 grams of NaCl in 1 mole. And so that means that if I were to take my 9 grams per liter and divide it by my molecular weight, that's going to give me 0.154 moles, or 154 millimoles of sodium chloride per liter of solution. And so you could do this calculation for any salt, as long as you were able to use a periodic table to figure out the molecular weight of the salt, and as long as you were able to determine, right, what amount in grams of that salt were present. So you need to go through and do a mole calculation, so grams divided by molecular weight to get to moles, and then you need to go through and, right, figure out the amount of liquid that you have, or water in this case, right, in order to be able to do a molarity calculation, so mole divided by liter. If we think about molarity and osmolarity in a little bit deeper of a context, if I wanted to know, say, for example, how many milliequivalents per liter of sodium are present in the solution, and then what is the osmolarity of this solution, we'd have to think about a couple of key principles. So the first thing we'd have to think about is the fact that an equivalent is the amount of a substance that will combine with or replace 1 mole, 1 gram, of H plus in a chemical reaction. So because H plus and Na plus both have a valence of 1, 0.154 moles of sodium would replace 0.154 moles of H plus. And that represents 0.154 equivalents, or 154 milliequivalents of Na plus. So 0.9% NaCl is going to contain 154 milliequivalents per liter of sodium. Now, each sodium chloride molecule then would dissociate into water as one Na plus ion and one Cl minus ion. And so 1 mole of NaCl is going to go to 1 mole of Na plus and 1 mole of Cl minus. So if I have 9 grams, or 0.015 moles of NaCl, and I add that to a liter of water, right, I'm going to produce 0.154 moles of Na and 0.154 moles of Cl, assuming that there's complete dissociation. So each liter of solution then contains 308 millimoles of non-dissociable particles. Osmolarity is going to be 0.308. How do I know that? Well, for every 1 mole of NaCl, I'm producing 2 moles of ions. I don't really care what those ions are. I just care about how many of those ions I'm producing. So if I go back up to this 0.154, right, and I multiply that by 2, that's how I get to my 0.308 osmoles per liter. So, right, that's again, going back to what we think about in terms of colligative properties, where it's dependent not so much on the identity, but simply on the number. And so you might be thinking to yourself, well, that's all well and good, but why do I care? So if we go back to what we talked about in terms of intracellular and extracellular fluids, and we think about water and where it's found, you can do a calculation to figure out the amount of water that is in a body, and then apply that percentage to figure out how much, say for example, is found. So if I had my 40 liters of water, right, I could do the calculation to figure out how much of that is intracellular versus extracellular. And I could then go back and think about, okay, so what's found in my intracellular fluids? Well, I've got cytoplasm, and I have some more proteins. I'm going to have a lot of potassium, as well as some ions and nutrients. And oh, by the way, I also have this 300 milliosmoles, right, or 0.3 osmoles. And, right, I could do the same thing for my extracellular fluids, recognizing that, right, I've got both plasma and interstitial fluid. And that is going to be high in sodium and chloride, as well as ions, nutrients, and waste. And again, this should also have this 300 milliosmoles. And that's important, right? Because I want my cells to be isotonic. I'm not looking for hypertonic or hypotonic cells, right? That would signal distress. What I want is an isotonic solution. And so if I think then, right, about what is a normal pH value for body fluids, right, it's going to be somewhere between 7.35 and 7.45. So ideally a pH of 7.4. So what happens if I exceed those values? Well, if the pH value of body fluids falls below 7.35, then a condition called acidosis results. And if that pH is above 7.45, then a condition called alkalosis results. So if I think about metabolism then, metabolism is going to produce acidic products that lower the pH of body fluids. So an example of that would be carbon dioxide. So as I respirate out carbon dioxide, that's going to combine with water and, right, form carbonic acid. And so another example would be lactic acid, which is a product of my anaerobic metabolism. And protein metabolism also produces phosphoric and sulfuric acids. And actually, my lipid metabolism would produce fatty acids. So these are all examples of ways in which, right, by going through metabolism, my body produces acids that contribute to changing the pH. These acidic substances have to be eliminated from the body in order to be able to maintain a pH homeostasis. If I have rapid elimination of acidic products from my metabolism, though, that can result in alkalosis. And the failure, right, to eliminate acidic products of metabolism would be what results in acidosis. And so those are two hallmarks that someone who is treating a patient would be looking for in terms of having a diagnosis and understanding what's going on in the physiology of that individual. And so I think it's important just to give context, right? Where would we see something like this? Well, we'd see metabolic alkalosis if someone's vomiting, or if in the case of a history of diabetes, we might expect to see metabolic acidosis. If there's a history of smoking or COPD, that would be something where we would expect to see respiratory acidosis. And as you go through this list, right, you're going to notice that there's a difference, right? There's both respiratory acidosis and metabolic acidosis. And you can think about how respiratory acidosis is going to be the byproduct of the production of CO2, right, and its respective products as it reacts with water to form HCO3 minus or H2CO3. Whereas the metabolic acidosis is from, right, the breakdown of proteins or fatty acids, from lipids, or a number of other examples where you're breaking down a substance and generating an acid. And so how do we diagnose this? So what we're looking for is the anion gap. So the anion gap is the difference in the measured cations, so our positively charged ions, and the measured anions, our negatively charged ions, in blood serum, in plasma, or in urine. And so the magnitude of this difference is what we refer to as the gap. So in serum, it's often calculated when trying to identify what's causing metabolic acidosis, right? So when the pH in the blood is lower than it should be. The anion gap is not actually directly measured by a lab test. In fact, it's computed using a formula that takes several individual lab tests, each of which measures the concentration of a specific anion or cation and combines them. And so the concentrations are expressed in units of milliequivalents per liter or millimoles per liter. And some examples, right, of a normal ion distribution, what occurs with metabolic acidosis due to acid accumulation versus metabolic acidosis due to HCO3 loss. And so one of the things that we'll be looking at then together as a class, right, is how you would go about doing this calculation and being able to understand the consequence of changes in these respective ions. And so this is fundamental chemistry that impacts the life and well-being of human beings as well as other living organisms. And so this gives you several examples of the types of problems that we're going to be solving in greater detail in class, as well as some examples of potentially assessment problems where I test your knowledge to understand what concepts you have grasped fully and what concepts we need to continue working on. So thanks again.